Hello guys, so welcome back to our third recording on lecture 19. So in that recording, we're gonna, flip the coin. So in the previous, recording, we did the analysis of the up-down counter. Now we're gonna design it so we're gonna pretend we don't have this circuit, and we're gonna, create it from scratch, build it from scratch, okay, or design it basically. So the question saying the following: design a 2-bit up-down counter using a more circuit with the flip-flop memory element. Okay. So the general procedure, for any design is these 6 steps basically. Although some of them will not be using in that particular example because the question forces us to use more circuit. Not melee, and D flip-flop, not T, not SR, not JK. Okay. So the steps are as follows. First, you choose what kind of approach you're going to follow. Is it a melee circuit or more circuit? Each one has its own pros and cons. We're going to explore these pros and cons at the end of this week, basically, second lecture. Okay. By example as well. Then we draw, we convert our ideas, the requirements that we're gonna implement, the functions that we want to implement into a state diagram. Okay. Based on that state diagram, we're gonna choose, or we're gonna know basically the number of flip-flops required, and then we're gonna choose their type. In that case, we're gonna find out only the number of flip-flops. But we are forced to use the flip-flop in such a particular example. But for practical design procedure, you are free to choose the type of flip-flops. Based on the state diagram, we derive the state table. And that state table is just like a truth table. So out of it, we're gonna get kernel maps and find out the equations that relates the inputs of the flip-flops to the current state and the input or inputs. You might have many inputs, X, Y, and also the output as a function of the current state and the input if it's a melee circuit, or the output as a function of the current state if it's a more circuit. Once you have the equations out of the kernel map, then you can implement. Then you know that you need, for example, 2D flip-flops. You need, or one, whatever, 1T flip-flop based on the design. You know that you're gonna need here an AND gate, here an OR gate, here an XOR, all such stuff, based on just the equations. Then you can build, the circuit by connecting the wires and the modules together. Okay. So let's explore the example now. So the first, step here is to, find the state diagram. Okay. Of course, it's melee or more, but we are forced here to use more. So we already, the question, it chooses for us what kind of circuit we should use or what kind of approach we should follow, which is a more approach. Okay. Now we build the state diagram. So it's an up-down counter, okay, that count from 0 to 3, okay? So it counts like this. So number 1, state diagram, or building the state diagram, okay? So we need a counter that count like 0, 1, 2, 3, then it goes back to 0 because any counter has a maximum, so it should reset afterwards. This is an up counting. For the down counting, it's 3, 2, 1, 0, then we go back to 3. It's a down counting. Okay. So there is a state in which we are 0, then we're gonna transfer to 1. There is a state called 1, and we're gonna go from it to another state called 2. Then from 2 we're gonna go to 3, then go back to 0. This is an up. In the down we have the same states but in an opposite direction. So you have 4 states. 4 states, that means you have 2 flip-flops, okay? Because each one will have one output, Q, like for example Q and QB. So you can build the 4 states. So we need 4 flip-flops. In that case, it will be the flip-flops. So let's convert that idea here into a state table. So it will be something like this. Zero, zero, 0, 1, 1, 0, 1, 1. Or let's say, yes, there is no, so it's better to, name them with symbols, like for example, S0, S1, S2, S3. Make it general. So we have a state in which the output will be 0, 0. The output Y is the output of the combination circuit, not the present state. And we have a state in which the output Y will be 0, 1, which is 1. And we have another state S2 in which the output will be 1, 0, which is 2. And we have a fourth state in which the output will be 1, 1, or 3. It's a more circuit. So whenever we are in S0, then the output will be 0, 0. Whenever we are in S1, the output will be 0, 1. Whenever we are in S2, the output will be 1, 0. Whenever we are in S3, the output will be 1, 1. We are forced to use more because the question asks us to do that, but we can use, of course, melee set, And we can move in 2 directions. We can go from S0 to S1, then from S1 to S2, then from S2 to S3, then from S3 to S0. Or we can do the opposite direction from 1, 1 to 1, 0, from 1, 0 to 0, 1, from 0 to 1 to 0, 0, or from 0, 0 to 1, 1. So basically, we need an input to determine the direction. Either we go counterclockwise or clockwise. We go up or down. We count up or count down. And for that, we just need an input, a single bit input. If it's 0, for example, we go up. If it's 1, we go down. Or you can choose the opposite. That's fine. You can do whatever you like. Okay? So we need one input bit. Yes, there is no one input bit to determine the direction of the counting. Either, for example, you can choose when the input, let's call it X, is 0, we count up. When the input is 1, we count down. One may say, can I choose the opposite? Yes, you can choose that when it's 1, you count up. When it's 0, you count down. Whatever you like. That's your choice, basically. So let's use this, new deducted information to complete our state table. I'm sorry, state diagram. So we chose that when X is 0, we count up. So if we are in S0 and the input is 0, we go to S1, in which the output is 0, 1, which is 1. If we are in S1 and the input is 0, we go to 1, 0, which is 2. If we are in S2 and the input is 0, we go to 1, 1. If we are in S3 and the output is 1, 1, and the input is 0, we reset to S0 again, which is output is 0, 0. If we are in 1, 1 and the input in 1, we count down. So we go to S2, in which the output is 1, 0, from 3 to 2. If we're in S2 and the output is 2, and the input is 1, we go to S1, in which the output is 1. then from S1 and we're in S1 we go to S0, and if it's 1, and if we are in S0 and then is 1 we go to 1 1 again. That's basically the complete state diagram. Okay, just one a single requirement that we didn't do yet. We said that S0, S1, S2, S3 are basically state of two flip-flops, D flip-flops basically, because it's a requirement here to use D flip-flops. Okay, state means value, 0 or 1. Okay, since we have 4 states, we need 2 bits. So you can choose whatever. So you have 4 combinations, 0 0, 0 1, 1 0, 1 1. So this is just a state. Okay, so you can choose S0 equal to 0 0. You can choose S1 is equal to 0 1, S2 1 0, S3 1 1. One may say, can I choose S0 to be 1 1? Yes, you can use it. You can do that. Remember, we differentiate the output from the state of the D flip-flops. Okay, so it's best here to use S0 equal to 0 0, S1 to be equal to 0 1, S2 to be equal to 1 0, S3 to be equal to 1 1. Why? If you do that, YA will be equal to QA and YB will be equal to QB. Okay, it will be very easy to analyze and implement as well. If you choose something else, you will have the second combination circuit in the output, which connects the output of the flip-flops or the memory to the output of the circuit Y, YA and YB. Okay, so but you can do it if you have resources. If you don't, if you don't care about much optimization in your circuit, you can do that. Okay, so the choice of the that's why I started by the symbols, because you are free. You are free to choose the state. Okay, so we're gonna choose for S0 0 0. We're gonna choose for S1 0 1. We're gonna choose for S2 1 0 and S3 1 1. And you can choose any other combinations for S0 to S3. I mean, you can choose S3 equal to 0 1, or S2 0 0, whatever you like, whatever you like. But this was the best. This here is the best. This will result in less hardware resources used in your implementation or your design, basically. Okay. Okay. So just add this little information to your state diagram. So S0 is 0 0, S1 is 0 1, S2 is 1 0, and finally here 1 1. And, it's a little bit compacted here, but when we show the solution, it will be the same. So let's look at the solution now. Let's remove all that stuff here, and let's look at the solution. Yes, that's just what I explained for you guys. Okay. So we need 2 bits because we have 4 different output counts, 0 1 2 3. Okay, so we have 4 states. It's 0 or S1, S2, S3, just names. You don't have to call S0 to S3. You might even call it ABCD, whatever. Okay, the choice, you are free to whatever you like. You can choose S1 equal to 1 1 or 1 0, but each state should have a different combination. You cannot choose for 2 different states same combination. For example, S1 and S2 0 0 and 0 0. No, that's forbidden. Now they are the same state. And To count up or count down, we need an input, 1 bit. If it's a 0, we count up, for example. If it's 1, we count down. And if you cannot choose the opposite. You can choose if it's 1, you count up, 0, count down, whatever you like. Okay. So let's check the state diagram. Here is a state diagram. With 0, we count up. With 1, we count down. Okay. Okay, that's basically the first step. The second one, let's erase all of this. The second one is basically to determine the number of flip-flops and their type. Their type is we are forced to use D flip-flops. If it's not mentioned in the questions, then we can use, you know, T for flip-flop or JK or SR. Okay, whatever you like. Although SR is not always good to use because of the forbidden states. Okay. And we will not use it. All the time we're going to use either D, T, or JK. And since here we have 4 states, each state is 2 bits, so we have 2 flip-flops as we mentioned, you know, when we start analyzing, you know, number 1. So we need 2 states, 2 flip-flops, and both of them are D flip-flops. Okay. Now, a third step here. Of course, that's also a very good observation. Using D flip-flops makes your job very easy. Okay, but that doesn't guarantee to use less hardware. But since D flip-flop is a transparent flip-flop, whenever the clock comes, whenever on the input will be reflected to the output, or the output will copy the input at the edge of the flip or the clock. That's why it's really easy to use D flip-flop. But that doesn't mean it will be the less hardware resource, the one that leads to less hardware resources. No, you might use D flip-flop in a circuit, and the analysis was easy, the design was easy, you know, simpler and stuff. But at the end, we got big circuit. The same design. You use the D flip-flop. Yes, a little bit complicated in the design process, but that might lead to less hardware resources or more compact circuit at the end. Cheaper one, basically. Okay. The state table. So let's check how I build this, you know, state table. It's really easy. Okay. Since once you have the state diagram, you can build in a very easy way the state table. Let's check how. For example, I did it in animation here. So, for example, when we are in S0, okay, so the present state is 0, 0, because we choose for S0 or S1, you know, whatever you call it, 0, 0. Then the output will be 0, 0. All what we need to do is to fill out this table. Of course, it's filled right now, but I'm showing you how to do it from scratch. Then, when the input is 0, so you put 0 here. You go to 0, 1 or S1. And for the same state, 0, 0, again, when the input is the outputs YA and YB will be zeros. Again, it doesn't change because it doesn't depend on the input because it's a more circuit. But when the input is 1, this time 1, we're gonna go to 1, 1. Look. So 0 is going to that way, 1 is going to that way. Let's change the color to make it clearer for you. So when the input is 0, we go that way. When the input is 1, we go that way. To 1, 1. Okay? And you're gonna do the following, do the same for all other, you know, for all other states. You're gonna find out that this column here is not filled. And I'm gonna show you how to fill it right now for each state. Look, we know that in a D flip-flop, when the clock comes, the output Q, the output of the flip-flop, not the output of the circuit, will copy the value on the D. What we did, or what we filled, for example, from in the first two rows here, we filled that part, that one, and also X and the QA plus, QB plus. We didn't fill the A and the B. But let's look at it now. Let's learn how to fill it. Let's start, for example, by DA. What does that mean that QA plus is 0? That means that when the clock comes, Q plus, copied what was in D. We know now QA plus, so it's basically the same as D. So D will be 0 as well. If QA plus is 0, then DA must be 0. Why? Because we said that when the clock comes, Q will be just equal to D. Whatever on D will be on Q. We know Q, so D will be the same. And same for QB and DB. For the second flip-flop, whenever the clock comes, the edge comes, QB will copy what was on D to be equal to D basically at that particular moment of the edge. So at that particular moment, since we know the output is 1, so basically that means that at that moment when the clock comes, DB was 1 also. And that's why D flip-flop is really easy to implement. Just make this. Note that Q plus is equal to D. This is basically the characteristic equation of the D flip-flop. If Q plus is equal to D, that means D is equal to Q plus, because now it is the opposite. Now we know the output of the next state, but we don't know the input. But you can just switch, get the right hand side to the left hand side, and what is on the right hand side to the left hand side. That's it. So D is equal to Q plus. So basically, copy this column into that column, and copy that column of QB plus to that column of DB. Let's take another example. Let's remove all that mess. S1. If we are in S1, which is 0, 1, and the input is 0, we're gonna go to S2, which is 1, 0. And whenever we are in S1, which is 0, 1, the output will be 0, 1 as well. Now let's get DA and DB before we go forward. That's really easy. Look, QA plus is 1. That means when the clock comes, there must be 1 also on the DA, so that QA plus is equal to 1. So it will copy D. So DA is 1. Let's do QB, DB. So QB plus is 0. That means when the clock comes, QB plus becomes 0. That means there was a 0 on DB as well. That's why we have 0 here. Now, when we still on, then another state, just an examples. If you are in S2, which is 1, 0, and the input is 0, we go to 1, 1. And the output will be 1, 0 all the time. Okay. See another examples. If we are in S3, which is 1, 1, and the input is 0, we go to 0, 0. And the output is dependent only on the current state, which is 1, 1, so the output will be 1, 1. And same story for DA and DB. You said that since QA plus is 0, that means when the clock comes, there must be a 0 in DA, so that QA plus copies this 0 and becomes 0. So DA is 0. Same story for QB and DB, QB plus and DB. QB plus is 0. That means when the clock comes, there was 0 on DB, so that QB plus copies the 0. to the flip-flop out. That's why we have DB is 0 here. Okay, that's basically how to build that state table. And based on the state table, the interesting step right now, which is since we have the state table, it's like a truth table. So we can get DA, DB, YA, YB as a function of the current state or present state, QA, QB, and X. Of course, this is Amelis again. This is a Moore circuit. So YA and YB, you will find them all the time only functions in QA and QB. Okay. So let's do that. Let's do, for example, DA. Here is DA. Where are the independent variables? These are our independent variables. And look, they are taking 8 combinations. And by the way, you can write it X, QA, QB, like what I did in the first example, or QA, QBX, or even QA, X, QB, or QB, X, QA, whatever you like. It doesn't matter. You must reach to the same, since you have the same state table, you must reach to the same equations, whatever the order of the QA and QB and X, the input X. Okay, so QB plus, or let's start by DA. So let's start by the first 4 values, 0, 1, 1, 0, 0, 1, 1, 0. Then second 4, 1, 0, 0, 1, 1, 0, 0, 1. This is basically XOR, you know. So you have 4 groups here, which is basically you will have it like this, you know, QA bar, QB, X bar, you know. But this is basically XOR, but for 3 variables. That's why I did. Whenever you have this scattered ones, and you cannot have a group of 2 ones together, this is basically XOR or XNOR. Okay, one of them. For example, if this is a shape, I mean 1, 0, 1, 0, 0, 1, 0, 1, this is XNOR. And if you have it like this, 0, 1, 0, 1, 1, 0, 1, 0, this is XOR. We have this here. So the A is equal to XA, QA, XOR, QB, XOR X. Let's do the key map for DB. Okay, so let's do that. 1, 1, 0, 0, 1, 1, 0, 0. Then again 1, 1, 0, 0, 1, 1, 0, 0. So we have one group here. This is basically QB bar. For YA and YB, I didn't do a key map here because they are really easy. Just look at QA and QB. You will find that this column here is exactly equal to that column. 4 zeros and 4 ones, 4 zeros and 4 ones. And this column here is exactly equal to that column. 2 zeros to ones, 2 zeros to ones. So you don't need to do a Carnot map. Save your time. If you wanna do it, it will be that. It will be QA and QB. YA is equal to QA and YB is equal to QB. Okay, that's basically the equations, the 4 equations. Once you have the equations, you can, of course, I'm sorry, yeah. Let's erase this. Once you have the, for this is just the groups, just to show you what are the groups that we have. And here is YA is equal to YB in graph, you know, animations, some animation for you. Once you have the equations, you have the implementation. So DA is equal to QA XOR QB XOR X. DB is equal to QB bar. And YA is equal to QA. YB is equal to QB. Let's start by YA and YB first. They are really easy. This is basically YA, just one wire. And that's it. So the combination circuit of the output is just one wire. Let's do DB because it's really also easy. It's equal to QB bar. Here is a QB. you can do it like this. Another solution, let's do it. It's because it's really interesting. Another solution for it is to do it like this. Look, this is a this is a D flip-flop. So any flip-flop, gives you the output and its complement at the same time. So instead of having QB and do the inverter, no, just take it from here. Both are correct. If you want to take QB, I'm sorry, here, QB and make inverter, that's fine, that's right, that's correct. If you want to use QB bar, that's also correct. Directly, without any inverter or something. Okay. Then DA is equal to QA, QB, and XOR X. So let's have the XOR first. Here is a QA, first input, second input is X, third input is QB. That's it. That's it. Let's check the solution. Yes, of course, because okay, let's remove first. Yes. YA and YB, the XOR here. And here is, DB is equal to QB bar. So you can do it like this, or as I said, you can do it from QB bar. Both are correct. Either this or this. Whatever, don't do both, just one of them. Okay. So that's basically, guys, is the second example. And as you see here, we reached exactly the same circuit that we analyzed, last time or last recording. Exactly the same circuit. Okay. And the flow of that solution here was exactly opposite to the analysis steps, the steps we took when we analyzed the same circuit. Basically, we started by this here, by this circuit, and here we ended by this circuit, or the implementation of this circuit. Here we started by the state diagram. There we ended by the state diagram. Okay, guys, thank you very much for watching this video, and see you in the next video. Bye.